Hey everyone, and welcome back to PrepFusion. I'm Manish, and again I'm back with the lecture of frequency response. So, previous lecture, what we studied, we basically studied about frequency response, basics of frequency response. When we give a sinusoid input, what type of output we get, and what are the different types of plot, and many related things about frequency response. But previously, I did one thing wrong, that I wrote the lecture number wrong there. It would be lecture 0 because that was the basics of frequency response. Now we'll go deeper into the frequency response, that is the frequency response of second order systems. So what type of response we get for a second order system when my OLTF is second order or my transfer function is second order, right? Which is for a unity feedback system. So that is what we'll learn here, and we'll learn a few more parameters by which we can define our response. And we'll just see, right? First, this is a block diagram of second order system. If we give some sinusoid input, uh, we'll get our frequency response as sinusoid only. If my system is LTI, here this is LTI, so this will get sinusoid only. But that response, whatever response we get, is known as frequency response if we give some sinusoid input. Okay, so let's see. This is my R of S. It may so happen sometimes we won't get a sinusoid response. What would be the case? We'll see. So this is R of S, and this time my R of S is what? Sinusoid input. Previously in time domain we did analyzed second order circuits there also, but what was my input? My input was varying. It was some time domain signal. It was not sinusoid. It was either unit step, unit impulse, parabolic, ramp. It was like that. We analyzed with that. But now what we are doing is we're giving some sinusoid input because we want to check the frequency response. So whenever we want to check the frequency response, we always give some sinusoid input. And when we want to check some time domain parameters, then we either give unit step response, unit impulse, or something along those lines. So this R of S is, let's say, like I've already derived it in the previous lecture, some a naught sine omega t. Now here my omega is the independent variable which is varying. It is the independent variable. There, what was my independent variable? My independent variable was time. Time, right? My independent variable is time. Here, omega is independent variable. That is why we were interested in the frequency response. That is why we plot, like I'll show you, that is why we plot with respect to omega in the x-axis, because omega is the independent variable. In time response we plotted with respect to time axis. There my time was my independent variable, and this response is can be written like c of j omega or c of omega, and this response is known as frequency response. This response is known as frequency response. Now, as I was discussing, right, that all the signals functions depend on time in the time domain analysis, and in frequency domain, all the signals and functions depend on frequency itself. They depend on frequency itself. Let me just go back to this side. Yeah, they depend on frequency. That is the difference of time domain and frequency domain. Here, omega is my independent variable. Independent variable, and here time is my independent variable. One, like there is relation between time domain and frequency. Obviously there is some correlation between the time domain response and the frequency domain response. The correlation we will study in the signals and systems chapter. Here we don't have obviously time. I'm talking about the subject. I can write my response, time domain response, like this: c of t Fourier transform. If we take the Fourier transform of my time domain response, I will get my frequency domain response, C of omega. Okay, so this is the response that I will get. So this we will study in the signals and systems chapter. So this I just wanted to give you a brief overview. So this is why like signals is very important, because it relates between frequency domain and time domain, because few information we can get from frequency domain very easily. If we just see the time response, we won't be able to decode that information. So let me just check if I am recording. Yeah, this is recording fine. We won't be able to decode that information. So now let's derive few parameters of the frequency response. First, we have already we have already written this in the time response chapter, that what is my transfer function. Transfer function is g of s upon 1 plus g of s. So this is the standard transfer function, right? Second order. So it will be omega n square divided by s square plus 2 zeta omega n plus omega n square. So my transfer function in terms of s. Now s is complex frequency, remember, and omega is normal frequency. Complex frequency, it contains the real and imaginary parts. So what is my transfer function? Transfer function is omega n square divided by s square plus 2 zeta omega n s plus omega n square. So this is my transfer function. Now previous lecture I told you at the end that we plot complex and now we plot the magnitude and the phase. Why do we do that? Because if we want to get the frequency response, we will replace s with j omega, and this transfer function will be some complex complex number, right? This transfer function will be some complex number. That's why we plot the magnitude and phase, because a complex number will have its magnitude and phase. Real number will only have, like, the magnitude will be equals to the number itself, and the phase can either be 0 degrees or minus 100 degrees, because it is lying on the number line, the real number line itself, right? But a complex number can have both magnitude and phase. That's why we plot it like that. I'll just show you here. So if we replace, so we'll put s equals to j omega. So what will this become? T of j omega equals to omega n square. Now this becomes j omega whole square plus 2 zeta j omega into omega n is also there, plus omega n square. Now this one becomes, just write this on normal, wait, omega n square. This is minus omega square. So this one becomes minus omega square. So this is omega n square minus omega square plus j into 2 zeta omega n. So what we are observing is we have a real component and an imaginary component in the denominator. Obviously this is a complex number, so this is a complex number. This is a complex number. So this is a complex number. This number will obviously have a phase and, oh no, just hold on a second, I have to stop the video because my iPad isn't again like working. Yeah, sorry, like don't know what happens. This tab keeps on getting crashed because this is getting work too much nowadays. Like constant, we are recording and teaching something and anything, right? That's why. So what I was telling is this will have a magnitude and phase response. So my T of j omega, and this is what in the frequency domain we are interested in. That's why we plot the frequency where we plot the magnitude also and the phase also. That is why in the previous lecture that is why I told that. So this will have some magnitude, right? Magnitude component, and this will plot with respect to what? With respect to omega. And here this will have some angle component, and this is also what will plot with respect to omega itself. So this is known as the magnitude response, and this is known as the phase response. So these are the two responses that we are mainly interested in. Okay, so now let's understand few things that, like, I've already given you the brief overview. So what we'll do, we have already got this function, right? We've already got this equation. So now we want to derive few things, derive the frequency response of second order system with the help of the transfer function. So we are mainly interested in the transfer function, and by finding the characteristics for the transfer function we will be able to find the response also. So first, this is the transfer function. So what I will do first is I will simply divide by omega n square. Simply divide by omega n square. Why? Because I want to compare my omega and omega n. You'll just see when I will do it. You'll just see. So first, let me copy this one. Just divide by omega n square. This one will become 1. This one will become 1 minus omega. Basically, we are normalizing it, right? Normalizing it. This is omega n square, and yeah, this is plus j to zeta omega by omega. We want to normalize it and we want to compare omega with our natural frequency omega n. That's why we want to see when omega becomes very high, what happens. Omega becomes very greater than omega n, and when omega becomes very less than my omega n, then what are the things that changes. That is what we are mainly interested in. So that is why we divide by omega n. Or if you don't understand, just understand that we divide by omega n. So okay, so now what we are interested in, we are interested in both magnitude and phase plot. So we'll write the equations of those two. So what is the magnitude? Magnitude is basically the real part square into imaginary part square. Simple. Numerator I have only one, right? So that is my magnitude basically. 1 divided by this 1 plus, no, this is not plus, this is minus omega by omega n square and another whole square plus 2 zeta omega by omega n whole square. Okay, so this is what my transfer function is, and obviously we can't forget the under root, because under root has the, at the end, right? Under root a square plus b square, that is the magnitude formula. So this is my magnitude. Now what about my angle? Mainly we won't be interested in angle, about the parameters, but let's just write the equation of angle also. So what is my angle? Like first, this is in the denominator, so obviously one minus sign will come, and my omega will assume that omega here is uh, less than omega n. Okay, so but whatever happens, my if my omega is less than omega n, what will happen then? This one will be something less than 1, so this real component will be positive and this imaginary component will be positive. So we're lying in what quadrant? We're lying in the first quadrant. Now if this omega is greater than omega n, if this omega is greater than omega n, then what will happen? Where will we lie? Then this will be more than 1, so real component will be negative and imaginary component will be what? Positive. Yeah, positive again, right? Imaginary component will be positive again. So if imaginary component is positive, then we are lying in the third quadrant. So then what will the angle will be? The angle will be 180 plus theta. 180, yeah, 180 plus theta. So just be careful about that. So we'll get two equations for angle. One equation is simply minus tan inverse imaginary upon real. So this is 2 zeta omega by omega n divided by 1 minus omega by omega n whole square. So this is the angle when what? When my omega is less than omega n. When my omega is less than omega n, then this one will be positive because this one will be less than 1. So this 1 minus something less than 1 is positive. Hence this angle will be something like this. Both of x and y are positive. Now what happens is, let me just reduce the size of this one. Now if my omega is greater than omega n, as I told, right, omega is greater than omega n, then this will be greater than uh, 1, and so it will be negative. So my angle will be 180 plus theta. 180 plus theta. Now what is theta? Theta is again this same thing, right? This same thing. Now as we are 180 plus theta and we have a minus sign also at the like this is in the denominator also, so we'll have to multiply a minus sign also. So this will be something like this, minus 180. Okay, I will write it here, minus 180, and just simply copy this, right? Copy this because theta is same. Theta was what? When both x and y was positive. So this is why theta. So this is the expression when omega, I'll just write here, like obviously if omega can't be negative, that we are assuming, so omega is greater than 0 and less than omega n. Not, will not write the equality signs. Now here my omega is greater than omega n, then this will be my equation. Simply like it becomes negative. That's the important part to consider here. And like what is the other part? Here we can see that like if we increase the omega, what will happen? If we increase the omega, my phase will always reduce. Why? If you increase the omega, this numerator is increasing and this denominator is decreasing. Because this minus sign is there, so this is decreasing and this is increasing. Overall this is increasing. So if this is increasing, so this is going in the negative direction. More reduction in phase. Here also the same thing again. If my omega is increasing, again it is going more in the negative direction. So here also the same thing is happening. So that is the important part. So these are the phase and magnitude equations for the transfer function of my what? CLTF, not the OLTF. This is the CLTF. Do remember that. That's why I am writing T and not G, because people always tend to get confused with T and G. Don't get confused. We are interested in the CLTF. Here I have written G, so I will change this to T itself. So now what we are interested in is when will be my uh, transfer function, magnitude of transfer function will be maximum, when it will be maximum, because phase is anyways always reducing, we are not interested. But what we can observe is this magnitude, right, this magnitude is increasing then again decreasing. Why? Because before this omega less than omega n, what is happening, this is uh, some small number, so this becomes 1, and uh, this also, if you're increasing from 0 to omega n, let's say if you're increasing from 0 to omega n, this is doing what, this is reducing this, right, and this is also increasing. Okay, but this is reducing, right, this is reducing, this is reducing. So this is reducing, then what is happening, our overall magnitude is increasing. Then what is happening, if now my omega is greater than omega n, if my omega is greater than omega n, what we can do is we can ignore this one. Previously what we did, we just subtracted this one with this one. Okay, then what happened, obviously this overall term got reduced. Now if the denominator is getting reduced, then what will happen, obviously the overall thing will be increased. But if my omega is much greater than omega n, what is happening, omega is much greater than omega n, then I can ignore this one, I can ignore this one, right? So I will just write this one and this one. So omega is increasing, what is happening, the denominator is increasing. Now this one is not coming into factor, this negative sign is not coming into factor, so this denominator is increasing. So if this denominator is increasing, then obviously my overall magnitude will reduce if denominator is increasing. So yeah, this is increasing then decreasing. So we're interested in the maximum point, wherever I am getting the value of magnitude maximum, and why we'll see. So let me just write it. Let me just copy this. There was one more reason to basically write this like this, right, divide by omega n, because we wanted to make the numerator clean. So now the numerator is clean and we only have the denominator. So when will this function be maximum? This function will be maximum when what, basically the differentiation of this one is 0, that is one case. Now when the numerator is minimum, when the numerator becomes minimum, the function becomes maximum. So that is what we're interested in. So what we'll do, we'll just take any function, right, take any function f of omega, who's interested in any function f of omega, and we want to make it minimum. Basically f of omega is this function, right, so f of omega is this function. So we can even take the square of this one, doesn't matter. Basically if the this function is minimum, then this under root will also be minimum, doesn't matter, right? So just have to take it, this is not less than 1, that is one thing we have to take care of, and it won't be. So let me take this function. Now what I'll do, I will just differentiate this one. So if I differentiate this one for maxima of magnitude of t of j omega, f of omega has to be minimum. So this is what we will do. So what is differentiation of this f of omega? So the differentiation is so we're simply differentiating it right now. Okay, so we'll apply chain rule. So can you tell me how many chain rules are here? There are, if you say 2, then you're wrong. There are 3 chain rules here. Just let us check. First, the outside chain rule. So this 2 will come here. Okay, like a to the power n is n into a to the power n minus 1. So this 2 comes here, and n minus 1 is 1. Now that is gone. Now we'll do the differentiation of this internal function. The differentiation of this internal function will be this one 0, and this 2 will again come here, minus 2 omega by omega n. That is done. Now again we have to do the differentiation of this internal function. So we have three internal functions here. That's why there are three chain rules. So 2 into 1 minus omega by omega n. Then we have minus, then we have omega by omega n. Yeah, then the internal chain function, that is 2 omega n. Now the another internal chain function, so this is minus 2, right? This is minus 2, don't forget, this is minus 2, and we have another internal function, that is 1 by omega, 1 by omega n. So this is 1 by omega n. So this is 1 by omega n, right? Now let's do the differentiation of the other function. Differentiation of the other one is simple. So this is 2 zeta omega by omega n, simply one chain rule, and again the inside function chain rule. So this is 2 into what? So this inside function has 2 zeta omega in itself, right? So this omega is the what? Independent variable. So this is 2 zeta omega n. So this is my differentiation, which should be equals to 0. Now can we cancel few things? What we can observe is we have omega n square here in the denominator, we have also omega n square here. So yes, we can cancel few things. We can cancel this omega n, right? 2 omega n square has been cancelled, as is equal to 0. That is not an issue. Omega n square is a constant, it's non-zero. That's why we can easily cancel it out. Now what else can we cancel? Can we cancel zeta square? No. Can we cancel 4? Yes. This 2 times 2 is 4, but minus 1 is still here, and this 2 times 2 is 4. So these are getting cancelled. So what I will do is I will take this on the right hand side. So if I take this on the right hand side, what do I get? I get okay, sorry, this one will be omega by omega n square, right? I forgot, because simply this is the outside function we are doing. Inside function we are not messing around with. Inside function I'm doing the differentiation in the next step, right? So yeah, I just missed one step there. So what will this equation become? This is 1 minus now I'm taking the right hand side, so sign has become positive now, into omega, and on the whatever right hand side, left hand side, doesn't matter, and this one is 2 zeta omega, 2 zeta square, 2 zeta square omega. This one is 2 zeta square omega. Now what happens? Now basically I will take the omega common. I can't simply cancel omega. Why? Because omega is a variable and omega can become 0. So can we simply cancel this 0? We'll see. Can we simply cancel omega? We'll see. So now we'll take it to the left hand side. So this equation becomes this equation becomes 2 zeta square basically. 2 zeta square is 2 zeta square. So this is minus 2 zeta square, and we have omega in common also. So what can happen here? What can happen? Either this can go to 0 and this can go to 0. So omega equals to 0 is a solution here. You can just simply cancel omega here, because if you put omega equals 0, this satisfies this equation. So you just can't simply cancel the independent variable. Just be careful in mathematics also. You don't cancel everything, right? Here I cancel omega n because omega n is a non-zero value. That's why I can simply cancel it. But whenever you're cancelling some variable x or something, be careful. If that is 0, then that also may satisfy the equation. Just be careful about that. So here we have two solutions. One is omega equals to 0 and another one is omega equals to what? So this one has to be 0. So I will write minus 1 by omega n square minus 2 zeta square has to be 0. Now we are mainly interested in this. Why not this? Because this represents this a DC signal. This is not a sinusoid signal. So we are providing some sinusoid signal. That's why we are interested in this one. So this will give me some non-zero value of omega. Now let's check this one out. So if I equate this one, what this becomes. So I will take omega by omega n square on that side. So omega 1 minus 2 zeta square is on this side. Here I have omega by omega n square. So my omega becomes omega n 1 minus 2 zeta square. So this is what my omega is. Now this frequency is also named as resonant frequency. Now why this is named as resonant frequency? Because my amplitude of my response will be maximum, because the magnitude is maximum, right? And the magnitude will get multiplied with the amplitude of the input sinusoid. So obviously the response will be also maximum. And if you have studied the network theory till now, we know that resonance condition is when I get something maximum, when I get some peak, right? That is when my resonant condition is. So if you have studied network theory, you will understand. So this is what my maximum is. Now what is the homework for you? The homework for you is whether this is true or not. How you can check? Basically you take the double differentiation of. So what is the homework for you? Although this is not like gate important, but still this can improve your mathematics skill, right? So you just check the double differentiation of f of d square of f of omega by d omega square is greater than 0 or not. Because for minima, what we check? For minima we check this is greater than 0 or not for minima, right? Because we want it to be minima, that's why my whole transfer function will be maxima. Just check this one. Okay, so this is the case. Now obviously my frequency can't be a complex number, so obviously it has to, like, this 1 minus 2 zeta square has to be greater than 0. So my omega r is a real number. If my omega is a real number, then obviously 1 minus, I will just write this in different color. So my zeta has to be what? Has to be less than 1 by root. So just be careful about this. So this is the condition for which we get resonant frequency. So obviously my system will be underdamped, but for getting peak resonant frequency at this, like for this expression, will our zeta has to be less than 1 by root 2. Now what happens if my zeta is greater than 1 by root 2? So if my zeta is greater than 1 by root 2, what will happen? My resonant peak frequency will be 0. My resonant peak frequency will be 0. So like basically at DC I'm getting peak, else I'm not getting. Equals to 0. Like from equation also, if you put in equation, you can check that putting equation, we can check, like if we put zeta equals to 1 by root 2, what will happen? This will become 1 minus 1 is 0, so omega r becomes 0. So these are the two cases. I will obviously write this, all this, we'll check this in like tablet format. You'll recall this, I will write this, but these are the few things that I wanted to tell you. Now this is one of the parameter. This is known as the resonant peak frequency. I will write the definition. I will explain the definition after a bit. But before going to the definition of resonant peak frequency, I want to calculate another parameter. What is the other parameter? Other parameter is the peak resonant magnitude. What is the peak? Maximum peak. So what is the peak magnitude? So maximum peak is written like this: MP is equal to what? Maximum of my magnitude at omega equals to omega r. So this is what my resonant peak is called. This is the resonant peak. So this is also another parameter. So these are the two parameters. This is another parameter that is not that important. I will also prove that, but these are the two parameters that you have to keep in mind, because mainly this will come in exam. This chapter is not that higher in weightage, but if you just remember these two formulas, you're good to go. You're good to go. So what about my resonant peak? So simply just put the value of omega equals to omega r in the magnitude function. So what was my magnitude function? This was my magnitude function. So just copy this one, or maybe I will not copy this one. So this one will be 1 minus omega. What is omega? Is equals to omega r equals to omega n into under root 1 by 2 zeta square. That is what we're mainly interested in. That we'll put. So this one will put omega n this one will also get replaced, so I will just reduce the size. So what will happen? This one will get divided, and now we'll square it. So this one will become 1 minus 2 zeta square. So this is on negative. So obviously 1 minus 1 gets cancelled, and I will remain with 2 zeta 4 zeta to the power 4. So just let me write it, else you will get confused. So my MP, maximum peak overshoot, not overshoot, resonant peak. So this is, as you can observe, exactly this one is getting cancelled. So this one, like I'm just simply squaring the 1 minus 2 zeta square, because this omega n is getting cancelled. So plus 4 zeta to the power 4. No, not 4 actually. Sorry, this will be 2 zeta square only, because this is under root, like this is under root, right? So that's why. Sorry. And this one will get square, right? So this one omega n will cancel. This one will become 4 zeta square into 1 minus 2 zeta square. So this one will come, and this one will become minus 8 zeta to the power 4. Okay, what else? Okay, sorry, here we have a square also. Sorry, we have a square also. Yeah, I forgot actually. We have a square also. So okay, this one is squared. So if this one is squared, so this one, that is what I was thinking, right? Something I'm messing around. So this one will become 4 zeta. So this one will become 1. And obviously I'm forgetting we have a under root also, so I will write it like this. We have a under root, right? So we have a under root also. So this becomes, we can take common zeta square. Also, I will just write this right now. 4 zeta square minus 4 zeta to the power 4. And this is under root, obviously. So here my MP, I can take common what? I can take common 4 zeta square. I can take common 4 zeta square. So if I take 4 zeta, so I take common this under root. So obviously this will become 2 zeta. 2 zeta. And here I have 1 minus, I am taking common 4 zeta square. So I will be remained with zeta square only. Zeta square, but don't forget the under root. Okay, don't forget the under root. So this is like we take common 4 zeta square. So obviously 4 zeta under root is 2 zeta itself, and this one is still remaining inside the under root after taking common. So this is 1 minus zeta square. So yeah, this is this. So now what is happening? Now basically what we'll do is we can derive another relation from this, which will be easier for you to remember. What is the relation? If you remember that what was my zeta in time domain response, what was my zeta? Zeta was equals to what? Cos theta. So what will be my under root 1 minus zeta? So what is 1 minus zeta square? If you remember, like 1 minus cos square is sine square theta. So under root will be simply sine theta. Under root will be simply sine theta. So we can replace this MP with what? We can replace this MP with 1 by 2 cos theta sine theta. And if you recall from your class 11 test, that's 2 sine theta cos theta was some formula of sine 2 theta. So this is 1 by sine 2 theta. So this is 1 by sine 2 theta. So this is what my maximum peak resonant is. But another thing what I wanted to write here is, so if DC gain of CLTF equals to KCL. What do we mean by DC gain? DC gain is when you put omega equals to 0. So if we put here omega equals to 0 in this equation, what do you get? You get 1 itself. So let's say our DC gain isn't unity, it is something else. If it is KCL, let's say KCL is a DC gain. Instead of K, I'm adding KCL because people will get confused with the DC gain of OLTF and the CLTF. So if my DC gain of CLTF is KCL, what will happen? It will just get simply scaled with KCL. Nothing. You just put the KCL, you will understand it for yourself. So if my DC gain is KCL, then my maximum, my peak resonant becomes KCL by sine 2 theta. So just remember this formula and the formula for the resonant peak, and that is more than enough. Don't go for the derivation, obviously, like there's no need of derivation, is for understanding how it came, but just remember these two formula and that's enough for this chapter. We'll do questions and from there we'll understand. So yeah, so just keep this in mind. The KCL is very important. Sometimes this is where the students will make mistake. You don't make mistake, and do remember this is the decision of CLTF, not the OLTF. K is different. K is the decision of OLTF, but they can define K for anything. They can define K for anything in the question itself. They can define K as a decision of CLTF. You don't get confused. You know exactly what my K is. My K is the decision of CLTF when you're solving the resonant peak problem, when you're solving this frequency response, second order frequency response problem, when you're solving some other problem, when you're solving the root locus problem, when you're solving the route problem, there K will be decision of OLTF. Okay, it may so K can be different, but you read the question and from there you understand what is my K. Very important, because K can be anything. K can be anything. So you can give name to anything, but you have to understand what does that object represent. That is more important. Name can be anything. That is more important. So now, like I have explained you few frequencies, now let's get a quick recap of different types of frequency. In the time response chapter we have studied two types of frequency. One was the natural frequency, another one was the damped frequency. Now what is the natural frequency? If you recall, the frequency at which the undamped system oscillates when some perturbation is given. Perturbation means, let's say, some impulse, certain impulse is given, to the system. Then, and if there is no damping, let's say if there is no friction, as I explained in the example of the time response chapter also, if there is no friction, then what will happen? It will just keep on oscillating. That is what natural frequency is. Basically the frequency of oscillation, the frequency at which it oscillates. If there is no damping, if there is practically no friction, then that frequency is known as the natural frequency. Now there is another definition of this natural frequency. What is the definition? For that, obviously we have to understand few things. So obviously this natural frequency will be for undamped system only. So if zeta is 0, then like what is my OLTF of my what is my CLTF of my second order system for undamped second order system? Transfer function undamped system. What is that? So it is T of S equals to omega n square by s square by omega n square. So this is my transfer function. Now if I give some sinusoid input whose frequency is equals to this omega n, what will happen? This is more important. So if by frequency is equals to omega n, this is what happens. Now if I give some in sinusoid whose frequency is equals to natural frequency, then what will be my response will look like? In Laplace domain, what you can observe, obviously this one will have a denominator term as s square plus omega n square. That is sure, right? And this one, my transfer function also has a denominator term s square plus omega n square. So I will get something squared in the denominator. And if there is something squared in the denominator, if you recall correctly in the first chapter, Laplace domain, so there is some multiplication in t. If you recall, right, there is some multiplication in t. So obviously my y of s will be in the something like this form. Y of s will be, or you can write c of s. Omega n square will be there. Obviously there will be omega n divided by s square plus omega n square, and there will be square term. So if there is square term, so we'll get some multiplication in t. We'll get some multiplication in t. So c of t some t times function of t. So obviously this will make the system blow up, unstable. So what was basically here, what was the input was impulse here. Now we're giving some sinusoid input has changed, so obviously the response will also change. So don't worry if you think here, sir, we are getting bounded input, it is oscillating, but here, sir, we are not getting bounded input, it is not oscillating. It is not oscillating at this particular frequency. Why? Like as from the Rajmach frequency. Okay, so this is the another second definition of my natural frequency. Here, in an undamped second order system, for a sinusoid input frequency at which the response of the system blows up is also natural frequency. At other frequency, it will not blow up, but at omega n, it will blow up because there will be some time multiplication time. Obviously, as time increases, this will blow up. So, in undamped second order frequency system, for a sinusoid input, the frequency at which the response blows up, basically goes to infinity, is not stable, is known as natural frequency. This is also the second definition of natural frequency. Just go through and that's it. Now what is damped frequency? The frequency at which my at which a underdamped second order system oscillates. Simple, right? We have an underdamped system and the frequency at which it oscillates around its mean point is known as the damped frequency. Now what is the resonant frequency? The resonant frequency, the frequency at which the amplitude of the response to a sinusoid input will be maximum. Like resonance, right? We want to get maximum amplification. If you remember in network theory, we wanted voltage amplification in series resonance circuit, we wanted current amplification in parallel resonance circuit. So here we want the maximum amplification. So that is why the term resonant comes up. The maximum amplification. Now do remember that this resonant frequency is valid for the condition that it should be underdamped and what? Theta 1 by root. And here what will be my maximum amplification? My maximum amplification will be peak resonant MP will be KCL by 2 not 2 sine 2 theta, or you can remember 2 zeta into under root 1 minus theta square, whatever suits you. Like this one suits me because I just have to write a single term. Obviously you have to find the theta. If you find theta, you will get, because like calculating the 1 minus theta square, that will take time in the gate calculator. You can use this one, just find theta and you will directly get the answer. But to remember, there is some issue with this one. When we'll solve question, we solve with both formulas, 2 zeta into under root 1 minus zeta square to zeta square, and this one we'll see like how to use this theta. Very important, we'll see. So yeah, now there is also one note: resonance in a control system is considered bad practice due to amplification of oscillation. So we, like, obviously we don't want to amplify the oscillations also. So what are oscillations? So basically I have an underdamped system, it reaches steady state, okay, at this value. So we want this steady state value, we don't want this initial oscillations, because these are very high from my stable value. So what will happen? It may damage my physical components in the control system, it may damage my components. That is what I don't want. This is my stable and it is amplifying my oscillations, that is very bad, it may damage my system. So if you have an electronic semiconductor component and the peak voltage that it can take is 1.1 volt. Now for some reason you give it some sinusoid input of resonant frequency and the oscillation, like it is an underdamped system and it oscillates certainly. So what will happen? Your initially what will happen? The time response, initially the oscillations will be, the amplitude of the oscillations will be much higher than, or it can damage my system. So that is why we don't want oscillations generally, right? Obviously we want amplification, but we don't want amplification like this. We want the steady state amplification and not this transient state amplification. Now here I've compared the time response and frequency response so that you can get a good idea, good relationship between the time response and frequency response. They are obviously interrelated with each other. Here for time response for under time system, my zeta will be between 0 to 1, and here for frequency response zeta will be between 0 to 1 by root 2. I will also give a table, and here we have a parameter named the maximum peak overshoot. This is also written as e raised to power minus 5 cot theta, and here we have peak resonant peak. This is 2 1 by 2 zeta 1 minus zeta square, or you can say k, right? You can say k here. So like to generalize this, KCL. KCL is a closed loop DC gain. And what are the things that I want to write here? Like just you remember this a part. Okay, this is the summary part. So means summary, that this is what you will need to remember. Okay, I will summarize at the end, or I will just copy it. First let me write this one, and I will just copy this one at the end. So what is the summary part? After this what we will derive, that is not that important, that also comes in exam, but these two are mainly important. So first is omega r. Omega r is simply equals to omega n for zeta equals to 0. So zeta is 0, obviously my resonant frequency becomes omega n. So if you put this like h cases in this equation, you will see that 1 minus 2 zeta square, and here our zeta is between 0 and 1 by root 2. Obviously if you put here zeta equals 0, this will become omega n, and if you put zeta equals to 1 by root 2, this will become 0. So obviously we're using the same thing only. This becomes 0. Okay, at DC I am getting resonant peak. So this is equals to, now what about my resonant peak? This was my resonant peak frequency. What about my resonant peak? So obviously, right, if zeta is 0 and if I am getting some omega n, obviously resonant, it blows up, it goes to infinity. Okay, it goes to infinity. You can derive the, that is homework for you, you can derive it, you can derive the transformation and just derive the response if you want to. So but don't have to waste too much time, because you have questions to practice, all those things to practice. So if you are very interested, you can derive that, else you just practice questions. So this one will become infinity for zeta equals to 0 at what, at resonant frequency, and this one becomes KCL by sin 2 theta zeta 1 by root 2, and this one is 0 when my zeta is greater than 1 by root 2. So this is what okay, no, sorry, this one is not 0, sorry. Like I'm getting DC, right? I'm getting my peak at DC, and what is the gain at DC? Gain at DC is KCL. That is the definition of KCL, right? It's not that KCL, not the Kirchhoff's current law. This is KCL inside. Okay, so yeah, this is what my peak resonance is. Now there is one more parameter, the cutoff frequency. This is also known as the half power frequency or 3 dB frequency. Why? Because at that frequency we are getting, my power of the signal is half. The frequency at which the magnitude response will be 1 by root 2 times of the DC response. So magnitude becomes 1 by root 2 times of the DC response, or at that my power becomes half of the DC power. These two definitions you can understand. So if my magnitude response becomes 1 by root 2, then in dBs what will happen? So like in dBs, calculating the gain in dBs for cutoff frequency. So this is represented as omega c. dB is how you convert to dB, simply multiply 20 log. So we will understand this in like a Bode plot specifically, don't worry. Which is to convert any absolute number to dBs, you just simply take the 20 take the log base 10 of that number and multiply 20 with it, so you will get the dB value. So this is like DC gain is this, and we have to divide it under root 2. So what you'll observe is this one will become 20 log 10 kcl minus what, this 20 log 10 under root 2, and that is equals to what, 3. Okay, that is equals to 3. So just keep that in mind, 3 dB. So obviously we're going 3 dB down, that's why this is known as the 3 dB frequency. So we're going 3 dB down. Okay, so this is basically the definition. Now here we will do the derivation. Okay, I will not do it in front of you because this will just take time, because this derivation is not that important anyways. So yeah, I'll just write down the derivation and then I will come back. Okay, so I have done the proof basically. So here is the proof. So first what I have done to simplify the equation, I have taken a unknown variable v, which is equals to omega c by omega n, to simplify my equation. Here okay, I don't have the, where is the equation? Here if you see, right, that here I had omega by omega n and all those things, so it will be difficult to directly solve it. So that's why I replaced this one with v. Now what I did, I equated this one with kcl by root 2. So at omega c, at cutoff frequency, so where omega c is my cutoff frequency, cutoff frequency, my DC my gain will be under root 1 by root 2 times of my this DC gain, right, closed loop DC gain. So I will equate this one, and if you equate this one, you'll get a quadratic equation. Now this will solve it multiple times in polar plot, so you should have good practice of this. So if I'm getting a quadratic equation and only even powers are there, okay, like this is here we have 0 power, so even powers are there, then what we can do, we can replace this even power with something x equals to v square. Now if you replace with this one with x equals to v square, then I'm getting a quadratic equation, and I can simply solve this. Now I'm getting x equals to this plus minus with it with the Sridhar Acharya formula. Now what I will do is I will ignore this negative solution. Why I will ignore this negative solution? Because obviously my cutoff frequency can't be imaginary. So ignore negative. Can be imaginary. My cutoff frequency can be imaginary. So if my cutoff frequency can be imaginary, obviously I will only take the positive solution. Positive solution. Now obviously what was my x? X was equals to v square, and what was my v square? V square was equals to omega c by omega n. So just simply replace like omega c by omega n, and you will get your cutoff frequency like this. Now this is the complete equation. What I will recommend is you remember only this one. This one is easier for you to remember if you want to remember. So it may also happen that you are not able to recall. You can like during the end of your exam, like just before the exam, right, last month of your exam, if you are stuck and if you like are not able to remember everything, then these are the few things that you can skip. This is the formula that you can skip. I'm not telling you to skip. If you can remember, obviously you have to remember, but this is one thing, this is on the lesser priority than the other those two formulas. So obviously those two formulas you have to remember no matter what, but this one you can skip if you're not able to memorize everything. So this is what my recommendation will be. So this is basically the cutoff frequency. Now these are the plots, right, for different values of damping. So here this one, as you can observe, this is going tending towards infinity. So here what is my damping? My damping is 0. This is the undamped system. Now as I'm moving this side my zeta is increasing. That is one factor. So if my zeta is increasing, obviously this peak resonant is also decreasing, right? Like this peak resonant is decreasing. So what is the value of this here? What is the value of damping here? As I can see, I am getting a peak resonant, right, which is not at DC. That means my zeta is between 0 to 1 by under root 2. So here my zeta is in this axis. Under root 2. So this is what my zeta is. So this, like you can say partial underdamped. Doesn't matter. Okay, I'm not writing anything. This you can say partial underdamped. Okay, because this is not completely underdamped. And here, what is my zeta? Here my zeta is 2. One is zeta is greater than equals to 1. Here my zeta is greater than equals to 1. Like 2, what do you mean by 2? Basically I have two types of damping here. One is the critical damping, another one is the what, overdamp. So just revising your few things, I'm not writing here, you can recall it. And also underdamp is also included. Sorry, not greater than equals to 1, sorry, greater than equals to 1 by root 2. So this includes the overdamped case also, the critical damped case also, the underdamped case also. Underdamped when it is zeta is greater than 1 by root 2. And this is my peak resonant frequency. The formula will be same here. You just put the value of zeta and you will get whatever resonant frequency you get. But just for this DC, right, just for this just for the critical damped and overdamped, all these things, the resonant frequency is omega r is 0. Okay, for this last line omega r is 0. Okay, so yeah, this is the basic summary of this graph. So I've drawn each of these graphs, right? Here zeta equals 0, this is the undamped system. Okay, this is blowing up, right? And this is my KCL DC can. And here we have underdamped system, and zeta should be between 0 to 1 by root 2, and we are getting a resonant peak. So this is the resonant peak. Can I mark this in the graph? Yes, I can. So this is MR, this is actually KCL, and this is KCL by root 2. This is the cutoff frequency. So this is the resonant frequency, this is the cutoff frequency. I've derived the formula. And also the cutoff frequency, like it can also be defined as bandwidth, because for a low pass filter that is how we define the bandwidth. Okay, so this is about the cutoff frequency. Here what was my resonant peak? My resonant peak was KCL by sin 2 theta. And what was my omega r resonant frequency? It was omega n 1 minus 2 zeta square. So these two things are very, very important. You have to remember this no matter what. This mainly comes in question. And like if my zeta is between this, then the response will be something like this. Okay, and they're just similar. If zeta is greater than this, so here like this is for underdamped, that's why I just differentiated this one. So this is for the underdamped case also. So here also this is underdamped, that's why I differentiated. But the response, right, frequency response, the transfer function response with respect to omega will be, magnitude response will be almost same for this and this. So here this is KCL. So here, right, this is my M resonant peak, and this is my omega resonant frequency. This is also MR, and this is also omega. Okay, so this is about here, right, I have two dampings. One is the critical damping, for zeta equals to 1, and another one is the overdamped. Overdamped just act as a first order system itself. Overdamped, zeta is greater than 1. So these are the few use cases of damping and the basically magnitude response. So I'll just quickly summarize, right? We just have to remember the formulas, nothing else. Okay, don't worry, we just have to remember the formulas. So I'll just quickly summarize this thing. Just copy, cut this one and paste this one over there, because that is the main crux of this lecture, right? So this is a summary. And the third parameter what you need to remember is this cutoff frequency. Okay, this is the least priority one, that's why I'm writing this in the third one. Okay, so this is the cutoff frequency basically. So this between this is for like zeta equals to 1 by root. I'm not okay. This is for any value because zeta can take any value because we're just generalizing it. Yeah, this is for zeta any value. Okay, so this is the cutoff frequency. So this is it for this lecture, and in the next lecture we'll solve a few questions regarding this chapter, and after that we'll finish this question chapter, because this is not that lengthy chapter. Basically just need to learn about these three parameters and that's enough. We'll solve questions and we'll see how to solve questions, because just knowing the formulas and how to use those formulas are two different things. So I will see you in the next lecture. Thank you for watching.